Hello everyone. Today I'm going to talk about result of Zedniak, Dvorak, Hu, and Sebastian-Sereni. They give a counterexample to a conjecture of Erdos-Rubin-Taylor. This conjecture is about the multiple least coloring of graphs. The conjecture was proposed in 1979, so it is old conjecture and attracted a lot of attention. Many people believe this conjecture. I believe this conjecture to be true, and but it turned out to be false. So it's a surprising result, at least to me. The paper is not long, but I think it's not so easy to follow the paper. By using the PowerPoint, I can have more ways. It's more convenient to show the construction of the counterexample. Hope this PowerPoint talk will be helpful. Okay, first I will define some notations. A k-least assignment is just assigns to each vertex a set of k colors. Given the least assignment L, and L coloring assigns to each vertex a color from its least, so that adjacent vertices get distinct colors. Now we say a graph G is k-choosable if G has an L coloring for every k-least assignment L. Now k-choosable implies k-colorable, but the converse is not true. Assume B is a positive integer and L is the least assignment, and LB coloring of G assigns to each vertex a set of B colors from its least, so that the color set assigned to adjacent vertices are disjoint. We say the graph is KB choosable if G has an LB coloring for every k-least assignment L of G. G is KB colorable if it is LB colorable where this L assigned all the vertices the same least. Now it follows from the definition that KB choosable implies KB colorable, but the converse is not true. This is a simple observation. K colorable implies Km M colorable for every positive integer M. Okay. So if phi is a K coloring of G, then you assign to each vertex this set of colors. Say this is a set of M colors. Then the total number of colors used is Km. So this is a Km M coloring of G. The conjecture we're talking about, which was proposed by Erdos-Rubin-Taylor, which says that we can replace this colorable by choosable. So the conjecture says this: k-choosable implies km m choosable for every positive integers k and m. So this was proposed by Erdos-Rubin-Taylor. So this is Erdos, this is Rubin, but I didn't find a picture for Taylor. This conjecture was proposed in 1979. It received a lot of attention. Many people started this conjecture, but there was not much progress. It was proved by Tooth and Foyt that the conjecture is true when k equals 2. That's every 2 choosable graph is 2m m choosable for every positive integer m. Now, in 2019, Dvorak-Hu and Sereni disproved this conjecture. They showed that for any integer k greater or equal to 4, there is a k-choosable graph which is not 2k2 choosable. Okay, so this is Dvorak, this is Hu, and I didn't find a picture for Sereni. Okay, so now I'm going to prove this result. The main part is to prove the k equals 4 case. That means we want to prove that there's a graph which is 4 choosable but not 8 2 choosable. So the first we'll construct the graph H and give an 8 least assignment L of H and show that H is not L2 colorable. Then this means that this graph is not 8 2 choosable, and then we show this graph is 4 choosable. So first we look at this graph. This graph I call it the H. You can say the vertices are of different shapes. Actually, the shape representing their least assignment. So the least assignment is defined as follows. Vertices of this shape, their least is 1, 2, 3, 4. Say these vertices, their lists, all these are all 1, 2, 3, 4. Now vertices of this shape, then is this 1, 2, 3, 4, 5, 6. Say these vertices have this list. And of this shape, that's 1, 2, 3, 4, 7, 8. This vertices. Okay? And these vertices have the 1, 2, 3, 4, 5, 6, 7, 8. These three vertices have this list. There's some other vertices, their lists are special. So like this one, the list is 1, 2, 3, 7. This is 1, 2, 3, 8. These are the lists of those special vertices. So now this is a list assignment. Every vertex gets a set of colors. So some vertices got 4 colors. The list size is 4. Some have list size 6, and some of the vertices have list size 8. Okay, so first we're going to show that this graph is not L2 colorable. That means we cannot pick 2 colors for each vertex from its list, so that the adjacent vertices get disjoint color set. So we're going to show this. So assuming this is not true, that means we have a L2 coloring of this graph. Then we look at these 5 vertices. They need to use at least 5 colors. Right? They need to use at least 5 colors for this. 4 colors are not enough to color all the vertices. They all have the same list. There's 1, 2, 3, 4, 5, 6. They need to use 5 colors from these 6 colors, at least 5 of them. Then this means that this vertex needs to use at least one of the 7 and 8 as its color, right? Because 5 colors are used by its neighbors, and they can use at most 1 color from here, and therefore it needs to use at least 1 from 7 and 8. Then this vertex also needs to use at least 1 of 7, 8, because if it does not use 7, 8, then because it needs the 1, 2, 3, 4, 7, 8. If it does not use 7, 8, it has to use 1, 2, 3, 4, and also this vertex has to use 1, 2, 3, 4. Then these 2 vertices together, they use all the 4 colors, 1, 2, 3, 4. Then this vertex has not enough color because the list is 1, 2, 3, 4, 7, 8, and he cannot use 1, 2, 3, 4. He has to use 7, 8, but 1 of 7, 8 is used by this neighbor. So now this means that this vertex has to use at least 1 of 7, 8. Okay. Now we assume that 7 is used here. There's a symmetry here, so we assume 7 is used here. Then 7 cannot be used by its neighbors, so these 2 vertices cannot use 7. Then you look at these 3 vertices. These 3 vertices, they have to use colors from 1, 2, 3, 4, 5, 6. And the colors assigned to these 3 vertices are piewise disjoint. Okay? For this vertex, it has to use 2 colors from 1, 2, 3. This vertex has to use 2 colors from 4, 5, 6. So the colors assigned to these 2 vertices are disjoint. And this vertex has to use colors from 1, 2, 3, 4, 5, 6 because that's the least assignment of this vertex. And it has to be disjoint from this color set of these 2 vertices because they are adjacent. So that means these 3 vertices use all the colors 1, 2, 3, 4, 5, 6. Therefore, this vertex has to use color 7, 8. These 6 colors have been used by the neighbors. It has to use 7, 8. And this implies that this vertex also has to use 7, 8 because you look at this vertex, this is the least assignment, but 7, 8 is used by its neighbor, so you can only use 1, 2, 3, 4. And this is also 1, 2, 3, 4. So these 2 together use all the 4 colors 1, 2, 3, 4. Therefore, this vertex can only use 7, 8. Now, for the same reason, this has to use 7, 8. This has to use 7, 8. This has to use 7, 8. Now, the important fact is that these 2 vertices, this vertex and this vertex, they both used 7, 8 as their colors. So 7, 8 cannot be used by its uncolored neighbors. That means I cannot use 7, 8 here. I cannot use 7, 8 here. And for this vertex, that's the least assignment of this vertex, and also I cannot use 7, 8 here. And this vertex, I cannot use 7, 8 here. So this vertex, I cannot use 7, 8. Okay, now, then this vertex, I have to use 1, 2, because this is the only two colors left. Right? And then this vertex I have to use color 3, 3, 4. Because 1, 2 has been used by its neighbor. Now, let's look at the remaining uncolored vertices. So you look at this vertex, the list is 1, 2, 3, 4, 5, 6. Right? 1, 2, 3, 4, 5, 6. But 3, 4 is used by its neighbor, so I cannot use 3, 4. And if you look at this vertex, the list is 1, 2, 3, 4, 5, 6. But 1, 2 is used by its neighbor, so I cannot use 1, 2. Now just concentrate on this 5 cycle. You look at color 1. Color 1 is here and is here. You don't see color 1 anywhere else. So therefore color 1 can only be used once, at most once. It cannot be used on both vertices, right? It can only used once. Similarly, color 2 is here, but nowhere else. Therefore color 2 can only be used at most once, and so is color 3. And for the color 4, 5, 6, each of them can be used at most twice, because no color can be used on 3 vertices, because 3 vertices, the 2 of them are adjacent. So now altogether, there are only 9 colors in total. Multiplicity are counted, but when multiplicity counted, we need 10 colors for these 5 vertices, because each vertex needs 2 colors, right? So therefore, this is I cannot finish the coloring. So what we have done, we have proved that this graph with this list assignment is not L2 colorable. But we do not have a graph which is not A2 choosable yet, because this list assignment is not an 8 list assignment. Some vertices only 4 colors in the list, right? Some of 6 colors in the list. Okay, so what are we going to do? So we continue our construction of the graph and the list assignment. So we take an arbitrary disjoint 2 subsets of this set. This is a set of 8 colors. So take 2 disjoint 2 subsets. Say maybe A is 9, 10, and B is 15, 60, for example. So then for these 2 subsets, we do the following. We add 2 adjacent vertices U and V. Now for each vertex in G that is list as size 4, so this is size 4, we add edges connect this vertex to both U and V. Okay? This X connecting X to both U and V, and they change the list assignment by adding A and B to the list. So this will become 2, 4, 5, 6 union A, union B. So now this vertex has 8 colors in the list. So this is a set of 8 colors. Right? We do this for each vertex whose list size is 4. Then for each vertex whose list size is 6, we add an edge connected to U and change the assignment by adding A to the lists. So this become this 3, 4, 5, 6, 7, 8 union A. So again, this L prime is a set of 8 colors. So now, after doing this, each vertex in here, or in the original graph G, has a list of 8 colors. Right? But U and V, we don't have list assignment yet. So after we have this a least assignment L prime, what we can say is that if we color U by color A, so assign this is A is a set of two colors, assign the set of A to this vertex, and assign B to this vertex, then this coloring cannot be extended to an L prime 2 coloring of the whole graph G, because the added colors, you cannot use it. They have been used by U and V. So this adjacent, you cannot use A, cannot use B. You have to use the old least assignment, but that we know already is not colorable. So this is true. Okay, so we take disjoint two subsets A, B. We put a copy of G like this. So this is a copy of G, but together with the least assignment. Okay? The least assignment is, so each vertex has a set of 8 permissible colors, okay? Using A and B in the list when they as before. Okay, then take another. So this is for AB. Take another two disjoint two subsets A prime B prime. We build another copy, and so this is built in the same way as before, except that instead of AB, I use A prime B prime. So now I have many copies of this G, and now for each two disjoint two subsets, we have a copy, okay? And so each of these is a copy of G, and all the vertices, each of them has a list of 8 colors. Then this is the graph H, and then I put least assignment for U and V. Say the least assignment of the lists for U and V are both this set of 8 colors. So now every vertex has 8 colors now. So this is L prime is 8 least assignment of H. We claim that this graph is not L prime 2 colorable, because if there is such a coloring, so you need to assign to U a set of 2 colors and assign to V a set of 2 colors, and this has to be disjoint. Whatever colors 2 subsets A, B you assign to U and V, there is a copy of G that cannot be extended. The coloring cannot be extended. So H is not L prime 2 colorable, and hence H is not 8-2 choosable. Okay, so we have a graph. This is the graph, which is not 8-2 choosable. It remains to show that this graph is 4 choosable. If we can show the graph is 4 choosable, then we're done. So we have a graph which is 4 choosable, but not 8-2 choosable. Right? So it remains to show this. So we assume that L is a 4 least assignment of H. We want to produce an L coloring of this graph. So how are we going to do that? We first actually color U by color from its list, and color V by color from its list. That is easily, we can do it. It's easy, we can do this. So after we have done this, then we're going to extend this coloring to each copy of G, to this copy of G, to this copy of G. Each of them is a copy of G, right? We're going to extend it. Can we do that? Can we extend? Okay, let's look at a particular copy of G. So this is a copy of G. Originally, each vertex has a set of 4 colors, because L is a 4 least assignment. But we have colored U and V by 2 colors, and the color of U and V cannot be used by their neighbors, right? So we have to remove the color of U and V from its neighbors. So for example, this vertex is adjacent to both U and V. So therefore I have to remove 2 colors from its list. So the shape of the vertices tells us how many remaining colors are there. We don't know what are the colors, but we know how many colors are there. So this vertex have 2 colors, and these have 3 colors, and this has 4 colors. Okay, so this is number of colors for each vertices. Okay, we're going to show that with that many colors for these vertices, we can color this graph. Okay, it doesn't matter what are the colors, just have that many colors, we can color it. Now we consider two cases. Case one is that we look at these 5 vertices. So case one is that these 5 vertices do not have the same list. Okay? In this case, we color this vertex with a color which is different from the 3 colors in this list. So this vertex, it has 4 colors in its list, and there's 3 colors in the list. So we can find the color which is not here. Okay, which is not here. Then after I color this vertex by that color, with that color, then this edge put no restriction on the color of this vertex because this color is not here. Okay? So whatever color you choose from the list, it's okay. So we can englobe that edge. Then we color these 5 vertices. Now we color these 5 vertices. We can do it because each vertex has 3 permissible colors, but there's one neighbor colored, right? So each vertex now has 2 colors. So each vertex has 2 colors. But these 2 colors, they're not all the same. Okay? They're not all the same. And it is easy to verify that in this case, I can color these 5 vertices. Okay? That's easily proved. Okay, I will not show that. You can do it by yourself. So I can color these 5 vertices. Now, after I color these 5 vertices, then I color vertices greatly in order. So how do I color this vertex greatly? First, I color this vertex. So when I color this vertex, it has 2 colored neighbors. And this vertex has 3 colors in the list, so I can find the color. I can color this vertex. And then I color this vertex. It has 2 colors in the list, and it's only 1 color neighbor, so I can find the color for this vertex. Then I continue doing this. I continue color the vertices in this order. You can easily check that whenever I color a vertex, the number of colors is of permissible color in the list is more than its color neighbors. For example, I'm going to color this vertex. I'm going to color this vertex. That's okay. And I'm going to color this vertex. It has 2 colors in the list and only 1 color neighbor. So I can color it. I can color it. I can color it. I can color it. Now, up to this point, I cannot continue color greatly anymore. I have to be careful. So what I'm going to do, I'm going to choose the color C1 for this vertex and color C2 for this vertex. I choose these 2 colors carefully. So how do I choose this C1 and C2? So if this vertex and this vertex, they have the same color, so they have a common color C1, then that is the color I choose. And assign C1 to this vertex and C1 to this, C1 to this, and C1 to this. Or maybe I cannot find such a common color. In this case, what I do, I choose the color C2, which is not in the list of this vertex. Because if they do not have a color in common, then they are disjoint. So each of them have 2 colors. Altogether they have 4 colors. They are disjoint, right? So, but this vertex is only 3 permissible colors. So there is a color which is not here. So that is the color I choose for this vertex. Okay, so after I choose C1, C2 in this way, then I can color greatly again. First color this vertex. I have 3 colors in the list, and I need only to avoid C1 and C2. So I can color this vertex. Then I color this vertex again. This is only 1 color neighbor. There's 2 colors in the list. So I can color this vertex. And then I color this vertex. This is okay because there's 4 colors in the list and there are only 3 color neighbors. Similarly, this vertex. Then I color this vertex. This vertex has 3 colors in the list and it is 3 color neighbors, but 2 of them got the same color. And I color this one, that's okay. It has 3 colored neighbors, but there's one vertex colored by color, which is not in the list. So I only need to avoid the color of these 2 vertices. I can have a color for this vertex. So now I color greatly again, then I finish the coloring of the whole graph. Okay. So this is finished proof of the first case. And the second case is that all these 5 vertices, they have the same list. Say, for example, they all have the same 3 colors, 1, 2, 3. In this case, I'm going to color this vertex again, but now I color this vertex by color, which is not in 1, 2, 3. It's a color which is not in here. That's I can find such a color because this vertex is a list of 4 colors. I can find such a color and color it. Now, after I color this vertex with alpha, then this edge put no restriction on the coloring of this vertex because the color alpha is not in the list of this vertex. So I can ignore that edge, right? Similarly, I can ignore these edges, right? Then I can remove this vertex because this vertex, it has 3 colors in the list and it has only 2 neighbors. So whatever color assigned to its neighbors, I can find the coloring of this vertex from its list. So I don't need to worry about this vertex. So what I just remove it. Now similarly, I can remove this, I can remove this. Okay, so I just need to color the remaining graph. Okay, so if I can color this remaining graph, I can color those removed vertices easily. Okay, so how I'm going to color these vertices? I'm going to color again greatly in order. So color this vertex, this vertex, this vertex, this vertex, this vertex, and so on. So you can check easily whenever I color a vertex, the list of that vertex has more color than its color neighbors. For example, I'm color this vertex. The list has 4 colors and it has only 3 colored neighbors. So I can choose the color for this one. And I can color this, I can color this, I can color this, I can color this. This has only 2 colors in the list, but there's only 1 color neighbor. So this way I can color vertex greatly in this order. Can color vertex greatly in this order. Okay. So now I have to be a little bit careful now. So I have 5 vertices to color. So every other vertex is colored. There are only 5 remaining vertices. You have to be careful. So let's check how many colors remains for each of these 5 vertices. So look at this vertex. It has originally it has 3 colors in the list, but it has a colored neighbor. So you have to remove the color of its neighbor from the list. So this vertex has 2 remaining colors. And similarly, this has 2 remaining colors because there's 3 colors in the list, but there's 1 colored neighbor. And similarly for this one, and this one. This one originally has 2 colors. So this is a 5 cycle, and each has 2 permissible colors. But look at these 2 vertices. They originally, the 3 colors for these 2 vertices, they are 1, 2, 3. And this 2 color is obtained from the 1, 2, 3 by removing the color of this vertex. And this 2 colors obtained from 1 to 3 by removing color of this vertex. And these 2 colors are different. They are adjacent. They are colored with distinct colors. So therefore, these 2 lists, they are different. Okay? So I have a 5 cycle, and each have 2 colors, but they do not have this same list. So therefore, I can color it. I can color this remaining 5 vertices. Okay, so this finishes proof. What we have proved? We have proved we have a graph we have showed that this graph is 4 choosable and which is not 8 choosable. And this result can be easily extended to this. So you can, for any k greater than 4, we can find the k-choosable graph which is not 2k2 choosable. Okay, how to do that? Well, we leave that as an exercise. It remains open about when k equals 3, when we don't know if there's a 3 choosable graph which is not 6-2 choosable, or 3m choosable for any integer m. So this is the end of this talk.